All right, these are the momentum concepts that we're going to go over for our forces test. First question is, what is momentum? Well, the equation for momentum is P equals mv. P is momentum, m is mass, v is velocity. Momentum is really just a property that objects with mass have when they're in motion. Sometimes it's been called mass in motion or as inertia in motion. But it's really just a property that an object has as opposed to something tangible like mass or speed. So it's a property that we use a lot when it comes to collisions, and it's very, very helpful. All right, a massive object runs into a stationary, less massive object. What would probably be the motion of the two after the collision? Well, the easiest way to do this is to take a look at it. So here we have the simulation. It was the lab that you had done previously. And what we got is a very large ball 1 here, and it's going to run into ball 2, so the mass here is 3, this one is 0.5, so you can see the big thing is going to run into little thing, and the initial speed of the red one is 1 meter per second. So if I hit play, it goes and hits the speed of the red one. You see dropped to 0.71, so it continues on in that particular direction, whereas ball 2 over here started moving real fast. So it would be typically what happens if a large object hits a little object. The large object is going to slow down, but it's going to keep moving in the same direction, and the small object is going to go flying. So the next question, a less massive object runs into a stationary, more massive object. What would probably happen? So let's reset this situation. We're going to change this mass to 0.5, and we'll change this guy to the 3. And if I play, here we go. And now you can see the little object hit and bounced away. The object that gets hit, object 2, is always going to move in the direction that it was hit. But when this is a little object, it typically bounces off and goes back in the other direction. All right, two people on roller skates are facing each other. They push off of one another. If one person has a mass of 100 kilograms while the other has a mass of 50 kilograms, what would their motions be like after they push off? Now, I know this picture has nothing to do with people on roller skates at first glance, but it actually does. So you have this really massive gun thing here, and it's firing probably a very large bullet at a really fast speed. But initially, before the bullet is fired, the total momentum is 0. The big gun has no momentum, the bullet has no momentum, just like the two people on roller skates. Well, in this case, you can see this gun is obviously way more massive than any shell or bullet that's going to be in this very large gun. So when you fire it away, you're giving a lot of momentum to that bullet because it's got some mass and you're firing it really fast. But momentum has to be conserved. So the gun gets pushed back in the opposite direction. It's called recoil. But you can see the bullet flies off and probably hits somewhere up on these mountains way back here because it was fired really fast. But this big gun only gets pushed back at the speed that you can see it. It's not flying off into the distance. And the reason is because of the mass difference. So when we talk about these two people on roller skates, this person who's got a 100 kilogram mass is going to get pushed back slower than the person with the 50 kilogram mass. And if you want to know exactly, since they've got twice the mass at 100 compared to 50, it's going to go half as fast. So when you have half the mass, you're going to go twice as fast. This is just an exaggerated example of what's going on here. The larger mass gets pushed back slower than the smaller mass, which is the bullet. What makes a collision an elastic collision? Well, here we have two people with the large yoga balls that decide to run into each other, and the guy being probably much more massive than the girl, she goes flying. So this is another example of if a more massive object hits a less massive object. Here's a water balloon smashing into this guy's face. Both of these we would consider in physics often pretty elastic, but they're not completely elastic. The textbook definition of a completely elastic collision is one where the kinetic energy is conserved. Now, it looks like kinetic energy might be conserved here in this situation because they bounce off each other with rubber balls, but you see this slow motion water balloon here smacking this guy's face, and you see how it got all deformed? Energy is going to get lost in internal energy of the deforming balloon and then reforming. So are either of these a totally elastic collision? No. But they're close because they bounce off of each other. An elastic collision, by definition, is one where the kinetic energy is conserved, but In physics, in this class, we typically say if it bounces off each other, it's pretty close. We can call it elastic, but technically it's not completely elastic. These would both be slightly inelastic because of the energy loss. What makes a collision an inelastic collision? Well, if an elastic collision is one where energy is conserved, an inelastic collision is one where energy is not conserved. And that's typically most collisions. But what we're going to say here in this class, and what most textbooks like to say, a perfectly inelastic collision, the most inelastic collision, is one where two objects are moving. In this case, you got the guy who gets the ball right here, and this other guy, and they hit and they stick together. So they hit and then they stick together because of the tackle, and that would be a perfectly inelastic collision without the kinetic energy being conserved. How do airbags work to help save lives? Well, here's a watermelon that got dropped onto an airbag, and you see that sort of cushions it to a stop, and the watermelon is okay. It doesn't break. But there it hits before the airbag opens up, and the watermelon gets all squishified. So here, hits the airbag. The watermelon's perfectly fine because it lands on this cushion of air. Whereas if it lands before the cushion of air shows up, it starts to break. So why does that work? Because the time that this watermelon is coming to stop is longer because of the nice cushiony airbag. So the time is big, so the force acting on it can be small. But if the time takes to stop right there is small, the force has to be really big, and that causes the watermelon to break. Here we have the Earth, and we have a little person that's going to represent all of us. And we are going to say, okay, we all jump up. Well, initially we don't have any momentum because in this question it says the entire population, we gather at one spot. This little person is going to represent us all, and we're all going to jump upward at the exact same time. Well, all the people are in the air with the Earth gain momentum in the opposite direction. Well, right now we have no total momentum because we're not moving compared to each other. But if we all jump up, yay, there we go. We all gain momentum in the upward direction. So in order for momentum to be conserved, the Earth must gain momentum in the downward direction. It's got to move. It's got to move downward. Now, because the Earth is so much more massive than we are, it's not going to move very fast, but it is going to move. So would the Earth gain momentum in the opposite direction? Yes, it would. Momentum has to be conserved. It's the law. And then finally, after the entire population of the Earth has jumped, here we're all the way up in the air, and we're going to land about a second or so later because gravity pulls things down, so we're going to get pulled back to the Earth. So after 7 billion people land on the planet, what's going to happen to the Earth's momentum? Can we knock it out of its orbit? Would it just be like it was before, or is it going to be something in between? Well, here's what's going to happen. We jumped up, but gravity is going to start pulling us back down. But as we learned, for every force there's an equal and opposite other force. There's an opposite reaction. That was Newton's third law. So if the Earth pulls us down, we pull the Earth back up. So it gains momentum upward. So we have momentum downward. It has momentum back upward. And those two momentums are going to continue to be equal to each other. They were equal when we left the planet, and they're going to be equal when we come back because force of gravity is equal on both of us. So our momentums are going to be the same. So as a result, if we have 1,000,000 worth of momentum going downward, the Earth's going to have 1,000,000 worth of momentum going upward. And as a result, we're going to hit and stop because the momentums are going to cancel each other out. And what that's going to ultimately mean is we can, all 7 billion of us, get to one particular spot on the planet and jump. The Earth is going to move a little bit in the other direction, but because of gravity, it's going to come back, and then we're going to hit and stop, and it'll be just like it was before. We cannot jump the planet out of its orbit.